Welcome everyone for being here. Today we are having Dr. Christine Andrews-Larson, and I'm so excited to have you. I have known her since 2018, so I have personal connection with her, and I met her during my PhD studies at Florida State University, and I had a chance to take her class during my studies. So I'm so glad for that. She's truly amazing human being, and just to orient the audience, her talk will take about 45 minutes. And as always, we will allocate 15 minutes to the Q&A session. So feel free to drop your questions in the chat box and we will address them during that final Q&A session. And after the talk, you can also unmute yourself and direct your question to our speaker. So without further ado, I would like to welcome Dr. Christine Andrews-Larson and introduce her background a little bit. And she's an associate professor of mathematics education in the College of Education and Department of Mathematics at Florida State University. And Dr. Andrews-Larson's work is broadly structured around three interrelated foci. First, she studies student reasoning and instructional design that leverages that reasoning. For example, in the context of inquiry-oriented mathematics instruction, particularly in the area of undergraduate linear algebra. And second, she studies supports for instructors to productively elicit and build on student reasoning. Finally, she is interested in exploring the ways in which inquiry-oriented instructional approaches may provide different kinds of learning experiences and outcomes for different groups of students. And her talk is titled "The Role of Social Positioning in Shaping Opportunities for Mathematical Activity in the Context of a Guided Reinvention of Null Spaces." So I'm just turning it over to you, Christy, whenever you're ready.
All right. Thank you so much. And thank you everyone for being here. I'm really impressed that 30 of you are here this late in the semester. I will admit when I reread the title that I sent you, Shada, I was like, oh my gosh, this sounds like the most boring talk. I wonder if anyone's going to come. I never put this many technical terms in your title, but thank you for coming regardless. So as I was writing my talk, I was like, all right, I guess I know which terms I'm going to have to provide some definition and context for. So I'll just give a little bit of background for this work. So I'm going to talk about what do I mean about guided reinvention, what do I need about null spaces, and I don't know if I can see if people do hands, but I'm curious. I know that there's a range of STEM backgrounds represented in this group, so I'm curious if we can do a show of hands. How many people are math? Can I see that somewhere? Okay, it looks like only one person raised their hand to that question. Hi, Bethany. And how many people have taken a linear algebra class at any point in their life? Just this is context for me because I'm bringing in an example that's relatively specific. Okay. All right, we have a larger number of people. So if you have not taken linear algebra, that is totally fine. I will try to give enough background that you can sort of follow the example from this talk, but I'm going to make the assumption that most of you don't know what a null space is, and that's totally okay. It's my goal that you can still get something useful out of this talk. So I'm going to talk a little bit about guided reinvention, null spaces, and mathematical activity. And for this group, I'm going to think of mathematical activity sort of as a specific instance, a mathematically specific instance of sort of disciplinary engagement. So I know in science, there's a lot of interest in disciplinary engagement. I think that's a nice crossover space. And then I'm going to talk a little bit about social positioning and why it matters. Because I certainly when I began transitioning from being a PhD student in mathematics to a PhD student in mathematics education, I did not have an appreciation for that issue. And it's taken me quite some time to get to the place where I think about it differently. So I want to frame this work in terms of a very widely cited study. So Freeman et al. In 2014 published a meta-analysis that included findings across 225 studies, and they looked at active learning in STEM, and STEM being science, technology, engineering, and mathematics. And they had to in looking across 225 studies, they had to sort of define active learning very broadly. And it almost is just anything that's not lecture, sort of fit that characterization. But what they did find is in those studies, the rates at which students got a D, an F, or withdrew from the course was 1.5 times lower than compared to lecture-based classes. And in those studies where they had a concept inventory for measuring student learning of core ideas in the course, there was almost half a standard deviation higher performance in the active learning group when compared to the lecture-based class. So this finding has been very widely cited. This finding has been very widely used to obtain grants to push for instructional change. And so I think it's a really relevant piece to sort of, I don't know, I guess everyone's on the bandwagon of citing Freeman, and I have been for a long time. And I want to think about a specific form of active learning. And so in mathematics, there's talk about what is often called inquiry-oriented instruction. There's also inquiry-based learning. Those historically are actually slightly different communities, but they're sort of coming to work together with a common set of aims. And then there's a very particular instructional design theory that underlies task design and sequencing within some components of inquiry-oriented instruction. And that's the work I'm going to be talking about today. So inquiry-oriented instruction aims to engage students in authentic mathematical activity by helping them, quote unquote, reinvent important mathematical ideas. So that's what I mean by guided reinvention. Obviously, if you look at history and an idea took hundreds of years to develop and you have 2 class periods, there's going to be some condensing and some modernizing of notation and language and context that students can make sense of. But so it sort of gives a framework for designing activities that facilitate learning in that way. However, when this instructional design theory is implemented in classrooms, social dynamics come into play and shape students' mathematical activity. So I'm going to be talking about an analysis of a paired teaching experiment. So this is just 2 students with a couple of teacher researchers as we're trying to develop some of these activities that function in the way that we hope. So the research questions for the study I'm going to share today is what's the nature of students' mathematical activity in the context of a guided reinvention of null spaces. If you don't know what a null space is, totally fine. We'll get there. And what is the relationship between students' positioning and their opportunities to engage in mathematical activity in the context of that paired teaching experiment? So I'm going to give you a little bit of background on realistic mathematics education. Realistic mathematics education is a tradition that comes out of the Netherlands, building on the work of Hans Freudenthal, who made the argument that mathematics is an inherently human activity and that involves reasoning about and organizing and notating and symbolizing and talking about context and solving problems in those contexts in particular ways. So mathematical activity could include things like quantifying, coordinatizing, symbolizing, defining, conjecturing, proving, justifying. And so those are the kinds of practices that mathematicians often engage in their professional work, and that when students are learning, they often don't engage in those kinds of practices until they're very advanced in their mathematical development. So this instructional design theory aims to make those forms of activity part of students' learning process. And there are 3 instructional design heuristics that are pretty central to the work that I'm going to talk about. So one of them is guided reinvention. So I pulled a quote from Stefan et al. That I thought did a nice job sort of explaining this. Some of what we consider to be basic mathematical concepts today took mathematicians decades or even centuries to fully develop. Students are expected to develop comprehensive conceptual understandings of mathematical concepts within the span of several weeks or months of a single school year. RME instructional resources help students reinvent these ideas in shortened periods of time using carefully sequenced problems and tools and guidance from the teacher. So that's sort of the big picture articulation of the goal for guided reinvention. The second heuristic is experientially real starting points for students. But I think that heuristic is relatively self-explanatory. The one thing I'll say is we say experientially real, not real, because it needs to be a context a student can imagine, not necessarily one they've actually experienced. So that's that choice of words. And then the third heuristic is emergent models, and that's going to be less central to what I'm going to talk about today. So I'm going to skip that part for now, just in the interest of time, but there is another heuristic that's in some of the more nuanced aspects of the work. So I'm just going to say a little bit about some research on student learning of vector spaces. So a null space is a particular instance of a vector space. If you look historically at linear algebra, you can think of the development of linear algebra as sort of being organized around the history that was pretty long ago, had to do with systems of linear equations and their solution sets. And there was a lot of theory developing that, going back into the hundreds of years BC in China. 9 chapters on the mathematical art is a lovely piece that has some really robust ideas and things that look very much like row reduction, which is a big part of students' first experience with linear algebra in modern courses. And then the other piece is vector spaces and mappings between them, which is a much more recent formal axiomatization of the branch of mathematics we refer to as linear algebra. And so vector spaces are what in the literature is referred to as a formalizing, unifying, and generalizing concept. So they take a bunch of different ideas and sort of put them together under a common umbrella. And so some core features of vector spaces is that they're closed under linear combinations. So the idea is you have a set of things that we call vectors. If you add 2 of them together, you remain in the set. If you multiply them by particular types of scalars, they remain in the set. And so those types of operations on those sets are really central to the notion of vector spaces that we want to really bring out for students. However, because they're abstract in nature, students really often struggle the first time they encounter vector spaces. And we've sort of narrowed in on null space as a type of vector space that is important in many applied fields, and one that we can identify some useful conceptual starting points for students to make sense of what is a vector space. So that's just a brief word on vector spaces. So thinking back to the research questions, the core questions that we wanted to look at: what's the nature of students' mathematical activity, and in the context of a guided reinvention of null spaces. And then the other question was, what is the role of social positioning? So I wanted to say just a brief word about how I'm conceptualizing mathematical activity and how I'm conceptualizing positioning, so that we have some shared understanding of what I mean by that. So mathematical activity, I'm drawing on Rasmussen et al. 2005 in using the term activity rather than thinking. And the choice of that language reflects a characterization of progression in mathematical thinking as acts of participation in a variety of different socially or culturally situated mathematics practices. So things like symbolizing, algorithmatizing, and defining activities are 3 examples of such social or cultural practices. And then in terms of positioning theory asserts that individuals draw upon and mutually construct storylines as they engage in conversation. So this is sort of assuming that this is a form of learning that isn't just an instructor, disseminating knowledge by giving a 50-minute lecture while students sit there and take notes. So this really takes up that active part of the learning where there's problems that students are supposed to work on and make progress on and reason about. And collaborative conversation is sort of imagined to be part of that progress. But when that happens, there is positioning that takes place. And so positioning a theory asserts that students mutually construct storylines as they engage in those conversations. And the storyline of school mathematics includes characters such as teacher and students and kinds of students, competent, slow, learning, disabled, disruptive, so on, and plots that organize what teachers and students can do. So for instance, a teacher can reprimand a student, but a student can't really reprimand a teacher. And perhaps students who are considered smart can tell others what to do. So you have these complex social dynamics that enter into the picture in these active learning settings. And there's further work you can look at that looks at students' identity development in STEM that is also quite consequential, but it's beyond the scope of this particular work. So I'm going to draw on this notion of positioning. Specifically, I'm going to be looking at the idea of authority and how that shapes students' opportunities to engage in mathematical activity. So just really briefly, the work I'm going to be talking about today comes from a team that I've worked with. Matt Montel, David Plaxco, Jessica Smith, Mina Kim, and Mark Watford have all been part of this. And then two other co-PIs on the project are Michelle Zandier and Megan Warrell. They're not on this particular slide because they're working on the inquiry-oriented linear algebra project, but they're focused on other instructional units. So just some background to our development of the instructional unit. So initially we wanted to develop a guided reinvention of vector spaces. And we sort of decided that that was too big, too much to take on. So we narrowed to subspaces, but really the part of that sequence I'm going to be looking at today is specifically around null spaces. And so the key ideas are this idea of closure under linear combinations and subspaces as sets that can be described as spans. So that gets into some linear algebra specifics that you may or may not be familiar with. And so we asked the question, what context can be helpfully solved using ideas about subspaces, null spaces, or column spaces? And networks where flow is conserved have non-trivial null spaces. And that's where we sort of got our idea. So our core task is an adaptation of sort of an electrical circuits context problem, but we wanted to move it to a context where students didn't need to have a specific background knowledge of electrical circuits and how they work. So we sort of moved it to a different context. Okay, so I'm going to talk about our problem setting. Our problem setting is that we have the hallways of one wing of a high school, and during a pandemic, this might have been something we worked on after 2020. We're changed to one-way corridors to promote social distancing, and the directions of the hallways are indicated by these red arrows. They connect. So this wing of a high school has 4 rooms. It's got an art room, biology room, civics room, and drama room. And each hall has a security camera that allows the principal to monitor student movement through the hallways. So we've got cameras 1, 2, 3, 4, and 5. And we also are going to assume that this wing is isolated from the rest of the school. And for now, we're going to assume that there's no going into or out of this wing. And before the school year starts, the principal goes in to the school to learn how to use the data from the camera system. And her daughter goes with her to help test the system by walking between rooms according to the one-way hallway rules. So her daughter, Ella, starts in the art room, passes camera 1, C1, as she walks from the art room toward the biology lab. And then she passes camera C2 as she passes from the biology lab to the civics room. And then Principal McDaniel sees the camera system has recorded the number of people who walked by each camera in the vector with the vector 1, 1, 0, 0, 0. So indicating one person passed camera 1, one passed camera 2, no one passed camera 3, 4, or 5. So that's how that information is encoded in the camera data vectors. And so I'm going to briefly switch over to my iPad just because I'm going to ask for, well, actually, let's see. I'm just going to keep going through. I normally would stop and make sure people are making sense of this. No, I am going to switch to my iPad. I'm sorry. I've changed my mind twice now. I'm going to screen share from my iPad, but if you would just take a moment and look at these two data vectors and describe the route or routes that Ella may have taken that correspond to the vector 33303 and 55323. And think about that while I switch to my iPad. You can assume that she started at room A, which might be helpful. Okay. So if you've had a moment to think and you don't mind typing in the chat, or you can raise your hand or just speak up. For the vector V, what path could that mean? I can't tell if everyone's being quiet and shy and polite, or if I am making no sense to anyone but myself. I feel like I'm back.
Just recalling, how you described. So I'm thinking for the vector V, the person passed through A, B, C, assuming that this person started from A. But then no person used camera 4, so probably they moved to art building, didn't use C4.
Right, so they didn't go down, so they went,
Yeah, and use the camera 5.
right?
Yeah, that's my prediction.
Now, and then, so that would be, if they just did that once, that would give us the vector 1, 1, 1, 0, 1.
Mm. Okay, in this case, probably this person, and this is the same person, so then maybe they did another round and another same round.
Right, so the 1, 1, 1, 0, 1 would be like the big loop around the outside, and then they did that 3 times. So we could either write that as 1, 1, 1, 0, 1.
Yeah.
Oops. Throw another one up there. Right. Yes, exactly. And then, so yes, that would mean that altogether, and like Beth said, that we would take that to mean that they took this trip 11101 plus 11101 plus 11101. So they make that trip 3 times, and that corresponds to the vector 33030. So similarly, if we had 55323, you might guess that they've got to pass camera 1 5 times, right? So if we,
Then that they took the diagonal twice.
you're guessing she took the diagonal twice?
Yeah.
Let's see. So right, if we
That's
have
why yeah,
if we have the 33303, and then if we take the diagonal twice, see where that gets us. That means we've got 1 1 0 1 0.
yes.
But if we do that twice, it'd be
Twice.
2 0.
0 2 0.
And we can see then we get the 3 plus 2 is the 5, the 3 plus 2 is the 5, 3 plus 0 is the 3, 0 plus 2 is the 2, and 3 plus 0 is 3. So these two vectors are really important for this task sequence. Specifically, both of them are what we sort of informally referred to as closed loop vectors. They're vectors where we start and end at the same place. And so we could even sort of denote them with a little square for the outer vector, or sometimes students will write B for the bigger loop. So we could write that as sort of 3 times those plus 2 of the triangle loop. Or you could call that T, or you could call it L for the little loop. Like, there are any numbers of notations that students can pick here to describe those. And then for camera data vectors you can't have, this is useful because it brings out that you have to have integer values. You can't have 1.5 loops. That doesn't make sense. You can't have a third of a person. And in terms of negatives, we assume negatives are not allowed, because if we did, that would sort of mean that we were breaking the one-way rules, is the assumption we make. So this is the version of the task that we developed after the paired teaching experiment, because it did a much better job of getting shared understandings of the meanings of how the data was encoded in the vectors. That was one of the things we learned in the paired teaching experiment. We had one student who was totally interpreting the encoding of data and vectors as we intended, and the other student was interpreting it pretty differently. We did collect data online. This was during the pandemic that this data was collected. So after that, students move on and they work on describing all of the different vectors that correspond to movement from room A to C of a single person, right? Which basically just ends up being any multiple of that blue vector plus any multiple of that pink vector. So any combination of those blue closed loops and the pink closed loops end up being that set of vectors. Oh, sorry, I lied. That's for going from C to C or from A to A. Those are the same set of vectors. And then if a single student went from A to C, like that 1, 1, 0, 0, 0 that we started with, we could take that path, and we could add any number of these closed loop vectors, and it's still a path from A to C as long as we add complete loops. So these for the non-math folks, these are all examples of linear combinations of vectors. We can add the vectors together. We can scale them by 3 or by 2. In this case, we can only scale them by positive or non-negative integer values. And so this builds to this idea of closure. What does it mean if a set's closed under linear combination? If you add things that are in the set and you get something that's in the set, then it's closed under the operation of vector addition. If you take something in the set and you multiply it by a scalar and you get the result that's still in the set, then we say it's closed under multiplication by those scalars. And that's a really central idea for ideas about vector spaces. So in terms of the task trajectory, after thinking about these sets of vectors that describe movement through the hallways, we have students do with a single person, with a group of 5 people. We then have them think about the relationship between the camera data vectors and the changes in the room populations. So for instance, this is our second task. So usually each task is would take a full day of instruction to sort of work through and come to discussion and agreement on. So we're doing the super fast version. So in this case, the principal wants to consider all the students who go past each camera between any 2 class periods, regardless of their path between rooms. So for instance, if between the first and second period of the day, these were the values registered by cameras 1, 2, 3, 4, and 5. We could use that information to think about how many more people or fewer people did, for example, the biology room have before and after the passing period. So it won't tell us the number of people in the room, but it'll tell us how much that number changed by. So for instance, if we know that 5 people walked past camera 1 and 3 people past camera 2 and 5 people past camera 3 and 4 people past camera 4 and 7 people past camera 5. If we just looked at the biology room, we could say, well, 5 went in and 3 went out. So altogether, the biology room gained 2 people between the first and second period. So in this case, right, we want to know what was the change in population for rooms A through D. So for instance, the change in A is 5 minus 3, or camera 1 minus camera 2. Oh, sorry, that was a change in B. If we want to look at the change in A, we see that we have 7 going in, past from camera 5, we have 4 coming in from camera 4, and we have 5 going out from camera 1. So in that case, we've got C5 number of people coming in plus C4 number of people coming in minus C1 going out. So 11 minus 5, or 4 plus 7 minus 5, which is way harder than it should be today, 6. Right, so room A gains 6. And similarly, we do that for room C and for room D. So this is starting to develop 2 different sets of vectors. One set of vectors that is the data vectors, and then another set of vectors that is our change in population vectors, right? So in this case, our change in A was 6, our change in B was 2, and if we similarly computed C and D, we can see we've got 5 in, 7 out, so D is going to be -2, and then we can also check C ends up being -6, and it's not by chance that you have this closed off wing, and your additional people, your people gained and people lost has to balance out across rooms, right? So all of this is establishing 2 different sets of vectors, camera data vectors, change in room population vectors, and a correspondence between them, right? So after doing a couple examples where students need to think about how can I calculate the change in room population, we have them start to think about what change in room population would corresponds to what set of camera data vectors. So for instance, this 6, 2, -6, -2 is not coincidentally the same as one of the ones they just found, right? So we know that if we have 5, 3, 5, 4, 7 people walking around, that room A, the art room, gained 6, the biology room gained 2, the drama room lost 2, and the civics room lost 6 for that particular set of camera data vectors. But if we added any of those closed loop vectors, we should have the same change in population. So there's multiple data vectors that map to this change in population. And that's sort of the idea that's being built up to. So I'm talking through a lot of this, but we have the students working through these ideas. And then I'm not going to spend much time on task 3, but on task 3, they have a different wing of the hallway. And through task 2, they build a matrix that maps those input vectors to the output vectors through the relationships that were sort of developed here, these kinds of relationships. You can develop a system of equations or a matrix equation. And in this case, they now have a matrix that produces that same correspondence, same kind of correspondence, but for a different wing of the high school. So that's the sequence of tasks. I probably spent way too long developing that ideas. But so we have these 3 tasks. First one, making sense of camera data vectors. Second one, making sense of population change vectors and relationships between those and camera data vectors. And then the third task, students are thinking about a new wing. And really one of the central questions is, what are the set of vectors that leave room populations unchanged? And that is the equivalent question is, what is the null space of a matrix? Basically. Now, the fact that we only use positive integers makes it not exactly the same, but the concept and a lot of those values are elements of the null space. So this is the sequence of tasks that we engage students in over a period of days to help them develop a guided reinvention of null spaces. So now I'm going to talk I'm running out of time rapidly. I'm going to talk briefly about our data sources. So we had a series of 4 90-minute online paired teaching experiments. And we also collected inscriptions created by the participants and the teacher researcher. And the goal was to see how students reason about ideas related to subspaces in the context of the task sequence, to understand their reasoning and to inform the refinement of tasks. So the versions of the tasks I just showed you are actually a little bit refined from the specific data set, but they're similar enough that you can make sense of what the participants did with what I'm going to talk about. And the teacher researcher had been the linear algebra classroom instructor, and their role was to elicit student ideas and to provide minimal support as needed to progress through the sequence. The participants were 2 white male students who we refer to with pseudonyms Drew and Carson at a predominantly minority public post-secondary institution in the southeastern United States. It was a small class where this data was collected, and those were the only 2 volunteers who were both 18 and older, which was an inclusion criteria in our study, and had taken a linear algebra course based in the Iola curriculum. So they had not seen this particular task sequence prior to the interview, but they had taken a linear algebra class. And it is incidental that both students had earned an A in the course. So that's just sort of the context for this analysis. So we had these video recordings of these 4 days of instruction. And so what we wanted to look at is the mathematical activity and its development across the sessions. And then the dynamics of the pair of students were such that we decided to do the positioning analysis. That was not part of the initial intent. And the basic dynamic was the intent was that the students would engage in each other's reasoning. What really happened was we had 2 participants who sort of worked in parallel and were quite resistant to engaging in one another's reasoning. But that was a little bit lopsided because one of them was quite confident and assertive, and the other one was much less assertive. And so that dynamic kind of played out. So this is sort of an analysis of what happened in terms of their opportunities to engage in mathematical sense making. So we have 90 times 4 minutes of pretty rich mathematical activity that we need to analyze. And so what we needed to do is we need to segment the data into a unit of analysis that would help us answer our research question. We settled on what we called episodes of mathematical reasoning, and this builds on the work of Lonnie Horn in defining and analyzing episodes of pedagogical reasoning. And what we did, so for each session, there were between 7 and 13 episodes of mathematical reasoning, and we ended up bounding those largely by the focus of talk. So it corresponded pretty closely to the specific mathematical prompts and when there was a shift in the mathematical focus. There were a few of the episodes that arose from something that wasn't in the materials, but most of them were in the materials. And then we created a summary of the mathematical activity for each episode of mathematical reasoning. And so we then conducted a first round of coding for the types of mathematical objects that students were paying attention to. We had a code book for that. And then we did a task analysis to look at the intended mathematical focus. I'll talk about that a little bit later. And then we did a second round of coding where we're trying to basically summarize the code. So we didn't code the transcript itself, we coded our summaries of the mathematical activity. And then for the positioning analysis, we spent a lot of time looking at the work of Jennifer Longer-Osuna. And she has some really nice work on student positioning and authority. And she's got a lovely code book. I think it's in her 2018 piece that we tried to apply to our data. And what we found is that the authority code at the level of the episode of mathematical reasoning worked very well. We had high inter-rater reliability and high rates of agreement between coders on that. Whereas when she had some other codes like bids or social authority as opposed to mathematical authority, there were a number of different things we tried to code for, but we could not get agreement. And part of it was the coding we were adapting was from a middle school classroom where students were working independently without a teacher coming by, and they coded those episodes differently. So there was too much involvement of the teacher researcher to directly use the coding scheme that she had. But so what we ended up doing is we just coded for authority. And then we did a second round of coding where we took our memos of the mathematical activity and we added positioning context for each one. And then for each session, we made a summary of what happened in terms of the positioning for each session. And then we read across those and we pulled out themes, either about particular discourse patterns emerging that was shaping the positioning or other trends. And then we sorted those in terms of where they seem to be coming from. So for the findings, this is the very abbreviated version. What we found is that one student he drew on the context to develop really robust, what I'll call loop-based reasoning. He used linear combinations of closed loop vectors, so the pink vector and the blue vector we talked about, to structure his reasoning about camera data vectors. And he reasoned that loop vectors corresponded to unchanging room populations. And that provided him with a really natural and intuitive way to reason robustly about the problem context as well as null spaces. In contrast, Carson, the other student, he really approached the task through his prior formal mathematical knowledge consistently across all 4 days. In the very beginning task, he had previously taken a course in graph theory. And so he had this prior conception of, when I see a picture like this, I make a matrix and everywhere a node is connected, I put a 1, and if 2 nodes are not connected, so if 2 rooms are not connected, I put a 0, and I make a matrix that way. So he was very focused on making a matrix, but what that matrix didn't capture the directionality of the rooms, and it didn't really capture this notion of like the camera data vector and how we were intending to encode information in it. So he was sort of focused on something different mathematically. And then when he did focus on camera data vectors, instead of structuring them as linear combinations of vectors, he made adjustments to the entries of individual vectors, which didn't have the same organizing power as using those closed loop vectors and separating them off as this closed loop vector plus this closed loop vector plus this other A to C vector. And without that organizing structure, the loop-based reasoning did not help him relate the inputs and the outputs in the way that lets the student see, oh, if I add closed loop vectors, it doesn't change my room populations. And that's sort of the core idea, that linking of input and outputs, that Drew was able to leverage really smoothly. And Carson did not reason in a way that was a natural connection for him. And so, but he did make frequent reference to formal ideas he'd previously seen, like linear dependence, the homogeneous equation, heavily used row-reduced echelon forms, which the row reduction process is something that was useful in the third task. And we actually saw a shift in the positioning when some of the prior knowledge he was bringing forward became really relevant for some of the conversations. So in terms of the positioning analysis, I'm going to separate the kinds of things that we saw into socio-mathematical, and mathematical issues. And so from a social perspective, we saw that one student had consistently higher influence and opportunity to engage in mathematical activity related to his own sense making across the paired teaching experiment. And we saw that in 68% of the 37 EMRs, he had high influence, and he also shared influence in all but, I want to say 11%. I didn't put that detail on this slide, but it was a very small percent where he didn't have high or shared influence. And the second thing that we noted is there was an emergent normative discourse pattern that really perpetuated this uneven distribution of opportunities for mathematical activity. And that was the interviewer would ask a question, the dominant student, Drew, would respond. And then the interviewer would ask Carson, the non-dominant student, what he thinks, and Carson would either agree or ask a question. So that became a very normative pattern across the 4 days of the paired teaching experiment. The second set of observations I characterized as socio-mathematical. And those have to do with the kinds of mathematical values or contributions that are really valued and taken up. So what we saw is that across the paired teaching experiment, situational activity was privileged, and that contributed to uneven opportunities to engage in activity related to students' own reasoning. So Drew kept reasoning in terms of loops, in terms of the situation. And because that was taken up, that is related to this high level of influence that we saw that Drew had. When the activity was more computational in nature related to row reduction, there was more equitable engagement in mathematical activity related to the contributions of both students. And then the mathematical activity that followed the teacher researcher's intended mathematical path was privileged. And then the last observation about positioning was that mathematically, and I've mentioned this before, reaching a shared understanding of how the data is encoded in vectors in the context played a really critical role in students' positioning and opportunities for mathematical sense making. So for my discussion, the number one thing that I see as a takeaway for this is that there is a dominant narrative in mathematics education research that student-to-student talk functions as a support for student learning. And while I do believe that that is sometimes true, I've had a lot of collaboration with my colleagues in special education of late, and I feel like their insights always give me new ways to think about things. And one of them is, I think we as a field need to reconceptualize student engagement in disciplinary argumentation, which may or may not, like group, that's what we often want group work to look like. But I think we need to conceptualize that as a learning goal rather than assuming that it functions as a learning support for all students. And then I also think there are some interesting things about a potential learning trajectory for the null space of a matrix, but given our distribution of humans, I'm going to skip that for now, and I'm also a few minutes over. So thank you for coming. Please share any questions you have.
Thank you, Christy. This was amazing. And thanks for sharing your research with us. We have about 10 minutes, and I would like to open up the floor for questions and comments. So, and I will monitor the chat as well. Feel free to unmute yourself or drop your questions in the chat box.
Can I ask a question about the results of your two participants?
Yes.
I was very interested, like as you were explaining how like different they reason about this topic. And I think I don't know, I might miss that part, but you were saying that Drew, the student, like one of the students, he was like making more reference to the topic of the null spaces versus the other students was making reference to outside knowledge. Um, so like what do you think like was the reason of this is like both of these students were taking linear algebra for the first time or
So their course taking background was equivalent, if not, I mean, Carson had taken a graph theory course that gave him another tool for thinking about these things. But so I would actually say it's not that Drew was reasoning about null spaces, it's that he was reasoning very explicitly in the situation. So he was using what I refer to as situational reasoning. And I didn't pull in a lot of examples because I chose to focus more on the positioning findings. But so often, right? So let me just go back to I'll go back to task 1, part 1. So the goal was in some of the things that they were asked to do is find a way to efficiently list all the camera data vectors that could be shown after Ella walked from room A to room C, for example, or from room C to room C. And so Drew answered in ways that sort of reasoned in the situation, right? Well, like, oh, we could have 1, 1, 0, 0, 0. And then he ended up writing something along the lines of like, oh, plus we could do the outer loop, which would be, let's see, 1, 1, 1, 0, 1. Right? But you could do that any number of times, right? So we could write it as any number of times we take that loop and any number of times we take this triangle loop 1, 1, 0, 1, 0. So this is the triangle loop, and that's the square root, right? So Drew reasoned in ways more along the lines of this. And then it's not this question specifically, but Carson would often bring in questions about like whether a set of vectors was linearly dependent or the solution to the homogeneous vector equation. And it wasn't always clear like how, I mean, I think often when students see applied scenarios, the assumption is that you should have already been taught what you know, and should be an application of a previously learned concept. And so often it seemed like Carson was sort of trying to figure out, which previously learned concept am I supposed to be drawing on right now, as opposed to, that you really want me to just make sense of this situation, and you're not looking for me to draw back on prior formal mathematical knowledge. So I think that's a good question, because then it's like, were the students working under different assumptions about our expectations, or were they just oriented differently to the work because that was what they were more comfortable doing? And I'm not sure I know the answer to that question, but I think it's a good one.
Thank you. I was also thinking like I think you mentioned about when the researchers were like asking the two participants and one of the students was like more like dominant than the other, which is like the student who was like making like more reference to the topic, the null spaces. I wonder also if that has to do with the same thing.
My intuition is that part of it was just personality, right? Drew was just more like, he's gonna confidently say what he thinks. But I think that there was a very strong, Carson was initially very willing to say what he thought, and that seemed to sort of decay over time, right? Because his ideas, not only were they not taken up, they were often corrected. in ways versus being worked with. Like, oh, that's an interesting idea. Let's try to make sense of it. So
Well, thank you for the wonderful talk.
thank you.
Any other questions? We have one question on chat.
Oh, interesting. AI could serve as a knowledge building partner that provides non-gentle judgmental feedback. Ooh, maybe. I've had some very interesting mathematical discussions with AI that make me distrust its expertise, and that make me nervous. So I'll just the first time I opened AI, I asked it a math question. It gave me an answer that was wrong. I told it was wrong. It apologized and gave me a different answer. And then there was like some subsequent back and forth, and like it used a mathematical term incorrectly, like it called a sequence a series or vice versa. And I corrected it. It apologized and it changed its language to be what's more conventionally defined as a sequence versus a series. Then 2 exchanges later, it made the same error. It felt like I was talking to a student. So I don't know, like, I think AI is susceptible to bullying, much like students are. So you can find things in the literature where, you may have a group where one of the students has a very good idea that is quite mathematically productive, but if they are not positioned to capitalize on that idea, it's often abandoned by the group in favor of whoever is loudest and or most popular. But maybe someday, I don't know, that maybe I don't think AI 6 months ago is necessarily the same as AI today.
We can get one more question. Actually, there was one question on the discussion forum I have with students, and Kateri, she had to leave early, but she was asking previously without seeing your talk. She has been curious on forms of active learning and what forms are more effective in classroom. And she's asking what forms of effective learning are there? Is there any, suggestion you would have for us?
Well, effective is there are a lot of ways you can think about what do you mean by effective, right? So there are a lot of things you can measure that you can care about and all that are legitimate, right? You can look at final exam grades, right? But if you have final exam grades increase, you how do you know that you didn't just write an easier final, right? You can look at, did students like the class? Did they feel like they belonged? Which may be different from and or intention to intention with, right? Some of the learning outcomes or the final exam grades, right? If you just make it easier and then students get better grades, maybe they like it more, but they aren't actually learning the content they need to learn. And so that is one answer to the question. It's not a very helpful one. Another answer to that question is, this is somewhat based on old research, but I still think it's a pretty good, well, it shapes my thinking a lot. And that is, there was a NCTM handbook chapter in 2007 that synthesized the research on sort of that question. What is the relationship between classroom instruction and student learning? And this was more at the K-12 level than at the post-secondary level. The basic answer was, in mathematics, you can look at that question through the lens of the type of learning that you're privileging, right? If you are privileging learning of procedures, explicit instruction, where there are multiple examples with, direct demonstration, fast sequencing of problems with multiple opportunities for success and fast feedback, right? Like that is what helps students quickly learn to execute procedures. So if that's what you care about, teaching that supports that is actually pretty well understood. The piece that is not well understood is supports for conceptual learning. And so supports for conceptual learning had, at that time, the promising directions had to do with the cognitive demand of the task, students' opportunities to learn, and attention to concepts and meaning. And so that's sort of the open question in the field. And there's been some work since then that I think is really good. So for instance, Bethany Riddle Johnston and at Vanderbilt and John Starr at Harvard have done some work looking at sort of bringing in this question, like, is explicit instruction or direct instruction an incompatible form of teaching with exploration? Because often people treat it as like one or the other, like direct instruction's bad and exploration's good, or vice versa. And what they found is that direct instruction and exploration support different kinds of learning. So specifically, they looked at middle grades math students' performance on solving linear equations. So I mean, this is not college level content, but what they saw is that exploration supported students in using multiple strategies, but direct instruction supported students in using an efficient strategy. So, which if you're going to pick an efficient strategy, it's helpful to know multiple strategies. But I think, so basically their argument was, why do we treat this as an either or question? These different forms of instruction support different kinds of learning. I don't know if that really answered your question, but I talked for a few minutes.
Thank you so much, Dr. Andrews-Larson, for answering all of your questions. And as we wrap up today's webinar, because of the time's sake, I just want to express my sincere gratitude to her for sharing her expertise with us. I particularly like the task you brought here today, and kind of, I think it showed me at least, the potential of inquiry learning, and just thinking how this looks like in classroom, the interaction component, and that, doing this with math students. So I appreciate the insights you shared from your research. It has been truly valuable. And I also want to thank each of you for being here, for your participation, and for your thoughtful questions. And if you have more questions or insight to share, feel free to reach out to Dr. Andrews-Larson. But until next time, take care. Thank you so much.
Thank you so much.